This is Sami Janin from the EPFL. Welcome to our MOOC on basic steps in magnetic resonance. Today we shall be talking about dynamic nuclear polarization, and this is going to be the first part of this chapter. This picture shows you one of the most famous DNP experiments. On the upper side here, you can see a spectrum measured on a urea sample with a single scan with DNP. On the lower side here, you can see the same spectrum measured without DNP with 200,000 scans in 65 hours. According to the authors of this paper published in 2003, the enhancement provided by DNP exceeded 10,000 folds. So the first question that is important to ask in this MOOC is, how insensitive is NMR? You probably know that if you have, let's say, milligrams of sample, sensitivity is usually not a problem, but if you decrease the amount of sample to, say, for example, 70 microgram, you might run into trouble. So in this MOOC, we're going to take as example sodium pyruvate labeled on the carbon 1 position, and we're going to assume, just for the example, that we only have 70 microgram of sample. Now if you measure this sample overnight in a 300 megahertz spectrometer, this is the kind of spectrum you're going to get in 128 scans at interval of 350 seconds and measured during 12 hours. Now, what if you want to look at the other carbons, those who are not labeled? So in natural abundance with about 1% C13. Well, this is the kind of spectrum you get. You see absolutely no signal because the signal to noise ratio only grows with the square root of time. So if you want to measure the same signal amplitude that you had measured on the labeled carbon, you're going to need 12 hours multiplied by 100 multiplied by 100, which amounts to 5,000 days, equal to 13.7 years. So who is responsible for such a low sensitivity? On the picture here you can see Boltzmann, and we're going to explain now why the low sensitivity of NMR is mainly due to the Boltzmann law. So you may have been told in some NMR courses or books that the thermal equilibrium density operator of the spin 1/2 can be described by Iz plus the identity. Well, in reality, there is a prefactor that describes the polarization in front of Iz. In the picture here, you see the two energy level of a spin 1/2. The balls describe the amount of populations of spins up and spin down. As you can see on this picture, there is almost as many spin up than spin down described by these big balls. Still, there is a very little amount of spins in excess on the energy level up with respect to the energy level down. And this is precisely what the polarization factor describes. The important thing here is that this polarization factor is usually much smaller than 1. So what happens when you do your NMR experiment? Well, you're going to drive transitions between those energy levels, but since you have as many spin up as spin down, it is just going to yield destructive interferences, leading to absolutely no signal. The only signal that you're going to get will arise from this very small amount of population in excess on one level with respect to the other, proportional to the polarization factor. Now what you would like in your NMR experiment is to have all the populations sitting on the same energy level so as to have a very high polarization in such a way that when you drive your transition, you end up with a very large signal. Unfortunately, the distribution of population at thermal equilibrium is described by the Boltzmann law. This Boltzmann law tells you that the ratio between the population and the two energy levels is described by an exponential law, exponential minus h bar omega, which is transition energy, divided by kT, which is the thermal energy. And from this law now, if you calculate the difference in population divided by the sum here, which is by definition the polarization, you end up with this formula, the tangent hyperbolic of h bar omega over 2kT. Now if you take your NMR sample and put it in a field of 7 Tesla, you realize that this polarization is very low at room temperature. At around 300 Kelvin, the polarization of your carbon-13 spins is only about 6 ppm. That means if you have 1,000,000 spins in your sample, only 6 spins will actually participate in the creation of a real NMR signal. All the other spins will yield destructive interferences that will not be observable. So there are two ways, according to Boltzmann, to increase the polarization. Either you increase the magnetic field, or you decrease the temperature. In order to achieve a polarization close to unity, you would need something like a mega Tesla, which is not practical. Or you would need something like a millikelvin, which is also very difficult to achieve. So another idea that was introduced by Overhauser is to rely on the electron gamma. The gamma of the electron is about 660 times bigger than for protons and about 2,600 bigger than for carbon-13. That means that the frequency is much higher, and that means finally that the polarization is also much higher. So what we're going to do is we're going to bring an electron and a nuclear spin together and try to transfer polarization from one to the other. So if you take your electron spin molecule, in this case a nitroxide molecule with an unpaired electron sitting on the NO bond, and on the other side you take your pyruvate molecule and you look, for example, at your protons, and you put this molecule in your field at room temperature, the polarization is still fairly low. Of course, the energy of the transition are quite different, and if now you bring the temperature down, you might end up in a situation where the electron polarization is high, for example, more than 90%, while your proton polarization is still very low. Now, how are we going to transfer polarization from the electron to the nuclear spin? Well, the first thing to do is to bring them together. You have to bring them in a contact such as you have, for example, a dipolar coupling, a hyperfine coupling, that will allow transition between those energy levels. How are we going to do that? How are we going to, for example, transfer the population here to this energy level so as to create a large nuclear polarization along this transition? This is going to be done by applying microwaves at the suitable frequency, and this is what DNP is about. In summary, we have illustrated how insensitive is NMR. We have described the spin polarization and explained why the sensitivity was directly related to this polarization, and we have shown that this polarization was very low in conventional NMR conditions. Finally, we have introduced dynamic nuclear polarization as a technique to enhance the nuclear polarization by transferring the high electron polarization to the nuclear spins by applying microwave, the ultimate goal being to increase the nuclear polarization to, for example, a value close to unity by having most of the nuclear spins sitting on the same energy level. Thank you for listening to our MOOC on basic steps in magnetic resonance, and thank you for listening to this chapter dedicated to dynamic nuclear polarization.